All right, we're going to take another look at invariant zeros. So multivariable poles and zeros, what we're looking at here. So recall that we can talk about system properties and properties of invariance. So for example, doesn't matter what we do to the transfer function, to the state model, we can do whatever similarity transformation we want, and the transfer function will remain the same. Similarly, the Hankel singular values are also system invariant. That is, they do not depend on the actual implementation or the realization of the system. Also, what's important is zeros, in particular invariant zeros and their properties. So when we looked at zeros before, we recall that we formed this matrix M of S given by this expression. So in this case, before we had S, which is A, B, C, D, minus E, minus S times E, where E was I and 0. Okay, so defining this matrix then, an invariant zero basically is a value of S, for example, S naught, such that this matrix drops rank. And we have seen this as a generalized eigenvalue problem. So when it drops rank, that means that either the right or the left null space has expanded. For our purposes, we're going to assume now that the right null space has expanded, but what follows could also hold if the left null space had expanded. So here we have a transfer function, and again, here we're showing it in continuous time. It holds just the same in discrete time. So here's our M matrix. I'm going to multiply it by a non-singular matrix, and given by this expression. And we can go through and show that this product gives us this expression. So we have A minus Si and H of S. So if the determinant of this for some value of S equal lambda naught, if that's non-zero, or in other words, if we don't have an eigenvalue, then the rank of this matrix will drop if and only if H of S, which is given by this expression, if and only if H of S drops rank. So a transmission zero is also an invariant zero. Okay, so we've kind of heard some things about that in the previously, but here we actually can, by multiplying all of this out. So notice that this is a non-singular matrix. So this matrix dropping rank is equivalent to this matrix dropping rank, because this matrix doesn't change the rank, okay, of this product. And so we have this. So whenever you have the rank of a product in general, it's possible that you can drop rank, but because this matrix is non-singular, it will not drop rank. Okay, and so we have this. And so again, this proves that a transmission zero is also an invariant zero. And so we saw that if the right null space is expanded, then there's a non-zero vector such that when I multiply M at some value S naught times that vector, I get 0. So if I look at this vector in terms of V1 and V2, if I divide it up this way, partition it, so here's M of S naught, that being equal to 0. If we assume that S naught is not a pole, that is, determinant of Si minus S naught is not 0, then this becomes two equations. The first equation says this. I can actually take this equation, so notice that I'm multiplying V1 times A minus S naught I times B. So V1 is equal to S naught I minus A inverse times B. So what happened to the sign? Well, because all of this had been over on the other side of the equation, when we take it to this side of the equation, this term changes sign, and so if we change the sign of this as well, we will get we get this expression. So C times V1 is equal to D times V2. So suppose our system starts with initial condition x0 is equal to V1. And suppose we apply the input e to the S0 t times V2. So that is u of s is in the Laplace domain is given by this expression. Then evaluating all of this in the Laplace domain, here is what x of s is in the Laplace domain. Si minus a inverse times x0 plus b times u of s. So notice that this times this is giving us a convolution in the time domain. Here in the Laplace domain, it's only a product. Since u of s is given by v of s over 1 minus s0, s minus s0, I can write it this way. And x0, if we choose the initial condition for x0 to be v1, we get this expression. Okay. But we've seen that v1 can be written this way. Si minus a inverse s0 I minus a inverse b u of v2. So I get this expression. And now I'm going to factor out this quantity and this quantity from this expression. So notice that when I factor out both of those quantities, this quantity, notice b2 appears in both of these terms. So I can factor out bv2 out. And so when I do all of this factorization, this term becomes s minus s0 times the identity matrix. And this term becomes s0 I minus a. So if you notice then, s0 i's cancel, leaving s minus a, si minus a. These two matrices are functions of the same matrix A. And as a result, because they are both functions of the same matrix A, they commute. So I can actually commute these two matrices. And so what that gives us then is this expression. These guys cancel. And the resulting expression then is 1 over s minus s0 times s0 I minus a inverse b v2. So that's x of s. So this takes into account the initial condition and the input. But all of this expression is equal to v1. And so we see that x of t is equal to v1 e to the s0 t. So x of t is given by this. So x is not a constant, it's not 0. It is itself also an exponential. And then when we look at y of t is equal to cx of t plus du of t, we see that x of t is given by this, u of t is given by this, and so I can factor out the e to the s0 t from both of these guys, and I get this expression. But this expression we saw was equal to 0 in that previous slide. So all of this is 0. That means starting with that initial condition and applying that input, y of t is equal to 0 for all time. And we've seen this before, so here we've seen it again, but now we're looking at it from the point of view of looking at it in the Laplace domain. Similar things would happen for discrete time systems in the z domain. So we had a non-zero input, non-zero initial condition that gave us an output that is identically 0. So that is a property of zeros. For a minimal system that is different than the poles, there exist constant vectors v0 or v not 0 or w not 0, so that both of these are equal to 0. Okay. Constant vectors. If for any 0 there exists a non-constant vector v of s and ws that are finite, such that the limit as s goes to 0 of this expression is equal to 0, and this is equal to 0 also. So we have these two relationships that also hold. For a finite invariant zero, S0, if the transfer function matrix is a full column rank, then the rank of this matrix will be less than n plus m. If the transfer function matrix is a full row rank, then the rank of this matrix is less than n plus p, where m is the number of inputs, here p is the number of outputs. And so we have some relationships between invariant zeros and the rank of the M matrix evaluated at that invariant zero. Stay tuned now for observers.